Okay, let's read through the problem. So for a machine shaft shoulder, okay, so it's shown here below. Small d is 1.1 inch, capital D is 1.65 inch, fillet radius is 0.11. The shaft is subject to a combined loading, a bending moment M, and a steady torsional load moment of T. The heat-treated shaft has an ultimate strength of 105 kpsi and yield strength of 82 kpsi. The reliability goal of the endurance limit is 0.99. We need to determine the fatigue factor for safety using a bunch of criteria. So D, Goodman, Gerber, Soderberg, ASME, and yield factor of safety. Okay, so one way of thinking about this is we can think of it backwards, which is uh, see what is required to compute the factor of safety. So this would be N, Y, and all of the other ones are N, F. So if you go back and see so for example, D Goodman, to compute the factor of safety, which is N, we need SE, SUT. We also need KF, KFS, MA, TA, MM, TM. And that's true for almost all of them. So if you go to Gerber, there is like SUT, SE, just to get this formula here, SUT, SE, Soderberg, and so on. So let's just try to list all the things we need to solve this problem. So we clearly need SUT, SE, SY, or all the dimensions would be important. We need KF, KFS. We need TA, TM, MA, here, TA, TM, MA, MM. Okay, this is just a straightforward application of the formula, but it seems like we need all these things. Okay, let's just try to list them out. So what do we know about the problem? We know the easier ones are the ultimate strength, 105 kpsi. The yield strength of 82. Sorry, 82 kpsi. We know the diameter. So D, capital D is 1.65 inch. Small d is 1.1 inch. The radius of the fillet is 0.11 inch. Maybe we're given steady torsional moment. So steady means Tm. So Tm is 1100 lbf inch. And then looks like we are given the bending moment. Since there's not said anything about whether it's being steady, I'm going to assume that it is actually the varying component. So it is 1260 lbf inch. Okay, and I would then assume that the non-steady part, the amplitude is 0, and then the mean for the bending moment is 0. Okay, so we are missing quite a few things. We are missing SE, KF, KFS. And I think once we get these three things, we should be able to complete the problem. Let's see if we can compute. Let's start with SE and then go for KF and KFS. Okay, so for SE is the endurance limit, and for endurance limit, we saw that there's like the whole lecture for computing that. Let's see that. So this is the endurance limit modifying factors. So the endurance SE is all these factors times SC prime. So question is, what is SC prime? I need to go one more lecture back. So let's see. Lecture, it was 17 maybe. Fatigue. Okay, here it is. So SE is found empirically. We need these formulas either in SI, IPS, or SI. So we are in IPS. I'm just going to grab this, copy. Okay. So now that we have that, let's compute SE. This is okay, so this came from 17 lecture in your notes. Okay, so now we need to compute, we need to see what SUT is. SUT is 105 kpsi, and 105 is less than 200. So SC prime is 0.5, 105, which is, I think, 62.5. It is 52.5, my bad, 52.5 kpsi. So we got that. Okay, now we need the endurance modifying factor, Ka, Kb, Kc. Let's see which of those we can compute. Let's start with Ka. Ka is, let's see, is surface factor. It depends on the finish. Let's go back to the problem and see what the finish is. We should get a hint from here. It's machined and also given heat treated. Machine shaft, heat treated shaft. Let's see what we're looking for here. Machined, just machined. Seems like that fits it. So for this is kpsi. So we need to use a factor of 2 for A and minus 0.217 for B. So Ka is A times SUT raised to B. And A is 2 and minus 0.217. And then SUT is 105. So 18. Okay, so that comes out to be 0.729. Okay, Kb is the next factor. Let's see what that is. So Kb is a size factor, which depends on the loading. So we know that we are looking at bending and torsion, but we have two options here, rotating round specimen and non-rotating round specimen. We'll just assume, since I don't think we are given anything about whether it's rotating or not, you can read it. I don't think anything given. So just make our life easy. We'll just assume it to be rotating. So for rotating specimen, bending and torsion, these are the formulas. We need IPS. I'm going to pick this. Copy. Let's go to 20. Okay. So this is picked from lecture 18. So we'll use KB Here our diameter is, let's see, is 1.1 inch. So 1.1 fits in this range, the first one. So 0.879, 1.1 minus 0.107. It's 0.87. Okay, next we need Kc. So let's see how to compute Kc. So go back to Kc. So Kc is a loading factor. For bending, it is 1. Torsion, it's 0.59. So really, we have two options now. We could use 1, or we could use 0.59. Okay. Uh, so if you use a large SE, so sorry, if you use one, what will happen? So between the two, one of them is bigger than the other. The one for bending is larger than the one for torsion. So the effect of using a larger value for Kc would mean that Se would be larger. And if you go back to 22 or 22 here, your factor of safety would be proportional to Se. Uh, so a larger Se would give you a larger factor of safety, and a lower Se would give you a lower factor of safety. Uh, so it's just a choice you need to make. Which of those you think is a better one you would go with. I'm just inclined, with just on my notes, I'm just going to stick with the uh, more conservative one, less conservative one, which is SE equals, well, I'll use the larger value. A larger value for Kc will give me a larger value for Se, which will mean a larger value for N. So it's going to be less conservative. So what I'm trying to say is that this is a design concern. It's like you want to make your design more conservative, go for it. Use 0.519. If you want to make it less conservative, then use the larger value. So let's say I want to make it less conservative, which will mean that I'll get a larger N, a bigger design factor, and that's what I want to go for. So going back, we have two values here. Let me copy this for your reference. Copy, and then put it here. Okay, so what we decided was um, SC, as you said, is proportional to Kc. Larger Kc will lead to a larger Se. Since N is proportional to Se, this was the formula I showed you here. Consistently, N and Se appear in the same side, so it's denominator, so it's proportional. So you'll find that since N is proportional to Se, a larger Se will lead to a less conservative design. So what we do here is we use Kc equals 1. Larger value, less conservative. So he's a bending one, in fact. So Kc is 1. Okay, let's move on to the other factors. We have Kd is the temperature factor. I don't think there was any mention of temperature in the problem. The temperature is assumed to be room temperature, so Kd is assumed to be 1. So Kd is 1. And the reason why I use Kd is 1 is because we assume this test is done at room temperature, or the or operating temperature is the room temperature. Okay, and then Ke is the reliability factor, which we can get from here. It should be a table. So we're looking at, see, what's the reliability? It says 99%. So 99% reliability is 0.814 for Ke. This is 99% reliability. So again, we see lecture 18 for that. Okay, so now we have all the factors. So now we are ready to compute SE. It's Ka, Kb, Kc, Kd, Ke, Se prime. Ka is 0.729, Kb is 0.87, Kc is 1, Kd is 1, Ke is 0.814, and Se prime is 52.5. Okay, so we are all set. Se is 27.1 kpsi. Okay, that's completes calculation of Se. Okay, now we've got this. Now let's go to Kf and Kfs. Okay, so how do we compute Kf and Kfs? First of all, do we need Kf and Kfs? So if you look at this geometry, you'll see that there is a change in geometry. It changes from capital D to small d through a fillet, and that basically introduces a stress concentration. So how do we compute Kfs? This is something we did in the past. So Kf is the fatigue strength of, well, not specimen. We had an algorithm to compute that. We basically use this method. So I'm just going to copy paste this so you have it for your reference when you are referring to this. Okay. Copy this. Yes, so this was taken from lecture, I think it's 19. Okay, so let's use this method to compute KFS. Okay, so first thing is compute KT, KTS from geometry. For that, we need to see A15. So A15 is a table in the, well, it's in the appendix. What I did here was I basically picked that up from the book. I'm just going to paste it here. Let me insert stress concentration. Okay, so this is the geometry here looks exactly like the geometry in the problem. So this is the one we need to use. This is, see if I can zoom it a little bit. Okay. Okay, so I have two of those because there would be one factor for bending M and there'll be one factor for torsion. So this one is, I believe, for torsion. So it'll be called I think it's called KTS here. And this one is KT, just for bending. So what do we need? We need capital D, small d, and R. So let me get those. So capital D is 1.65, small d is 1.1, and small r is 0.11. 0.11, all in inches, so inch, 1.1 inch, capital D is 1.65 inch. Let's compute the factors of interest. Here we're interested in computing capital D divided by small d, so 1.65 divided by 1.1. That's 1.5. And then small r divided by small d, that's 0.11 divided by 1.1. That comes out to be 0.1. So that's all we need. Let's try to pluck the KT from this figure, KTS from the figure. So for KTS, let's look at the line for 1.5, different color. Okay, so we have 1.09 here, 2, 1.2, 1.3. Okay, so we don't quite have 1.5. So we'll have to sort of interpolate between 2 and 1.33, which is okay. The lines are so close, so it's probably, you can choose one of those. If you look at R divided by D, then it's 0.1. So this is 0.1. So we are looking at this line, and then either that point involving cap 2 or 1.33. So it's approximately here. Okay. I mean, I would say this is 1.6 for sure. So it's somewhere between 1.4 and 1.6. It's really up to you. You could just make it 1.5 if you want. In my notes, I actually have a more precise value for this. It's actually a little down. It's close to 1.4 than it is to 1.6. What I got here, or what I assumed, is 1.42. And as I said, that's not, if you got this problem in the exam, you don't really have to assume 1.42. You can assume 1.5. Anything between 1.5, I think, 1.4 and 1.5 should be fine. Okay. That's the value we'll use. Okay, now we go here for KT, and then again, 0.1 is this line. And it intersects 1.5. So we have 1.5 is available. It's right here. So it's basically this. It's actually slightly down, I think. Yeah, it's slightly down. It's not exactly at over here. Yeah, I have a value from my notes. It's 1.68. Let's just stick with that. So my answers would be right. It's not very important to have the exact value. So don't worry too much about that. So I got 1.68. Okay, so that's that. So what we've got from this is KTS is 1.42, KT is 1.68. We'll use this. So if you go through our three-step algorithm, compute KT, KTS, this is step one. Step one, which is done. Next, we need to compute Q and QS from the figure. So what we did is, well, actually, there are a number of ways to compute Q, QS, but what we'll do is we'll use the plots. So I'm going to insert the picture, insert. So this is a plot for Q. Okay. And then there's another one for QS. Okay. So next is to compute Q and QS. And for that, all we need is the ultimate strength. So we need the notch radius. So R is 0.11. And then we need the ultimate strength, SUT. So for this problem, SUT is given as 105 kpsi. Okay, so we need to probably eyeball this also. So R is 0.11, so here. And then we go all the way up to SUT of 105. So if we've given 100, this is 100, this is 0.1, so we're looking at this point approximately. Okay, so that looks like it's above 0.8, less than 1. It looks like it's somewhere between 0.8 and 0.9. We just assume it to be midway between those. So 0.85, this is the value of Q. Okay, now we need to compute the same one for QS. So again, 0.11. 0.11 is here. SUT 100 is given to us. So it's probably, so it's this line right here. It looks like it's again between 0.8 and 0.9. I actually assumed the same as this one. So Q is 0.85. Okay, so QS and QT are both 0.85. This is QS. So Q equals QS is 0.85. So this completes part 2. And the third part is compute KF and KFS using these formulas. So we know KT, we know KTS, and we know Q and QS. So we can compute KF and KFS. So the third step is KF is 1 plus Q times KT minus 1, 1 plus 0.85. KT was 1.68 minus 1. So KF is 1.58. And then KFS is 1 plus QS, KTS minus 1, 1 plus 0.85, 1.42 minus 1. So KFS is 1.36. Okay, so we're done with KF, KFS. Okay, now if we go back to our list of things to compute, we have done this and this. And now the last step is to compute N for A through E. So we just need to go through these formulas. D. Goodman will essentially take this formula. Okay, let me call these, call this 1, and then call this 2, call this 3, call this 4, and call this final one 5. So essentially, this boils down to us taking these formulas for 1 through 5, substituting the value for small d, SE, SUT. Let me do one for you, and then other ones, I will just write the final answer. Copy. So this is A from 1. So you need to use t equals 1.1 inch, SC equals something we computed. Let me just find it here. SC is 27.1 kpsi given to us. Well, we computed that. SUT is 105 kpsi. Kf, we just computed that. Kf was 1.58. KFS was 1.36. MM was 0. TA was 0. MA was 1260 lbf inch. TM was 1100 lbf inch. Yeah, I think that's all you need to compute N. Don't think I'm missing anything. Okay, so using Formula 1 and all these values, N comes out to be 1.52. So this is T. Goodman. This is answer to part A. Part B, again, do the same thing. Use the second formula to compute N equals 1.73, C N equals 1.46, T N equals 1.74, E, this is the first yield, N equals 4.5. So these came from 1, 2, 3, 4, 5, and they were T. Goodman, D. E. Gerber, D. E. Soderbergh, D. E. Semi elliptic, and then finally first yield. And then you can see that this is the most conservative. It has the smallest factor of safety.